Welcome back. Today we're about to begin our new unit, Unit 2, the rational to the real to the complex. You're going to need your graph notebook, your new packet, a erasable pen or pencil, and a ruler. Got 'em? Great. Let's take a quick scroll through our new packet here. First thing you always have is the table of contents on the front, as well as inside. Remember, this is your research journal. There is a very extensive vocabulary list, which we'll be practicing during this unit. And here is our first lesson. Our first lesson is about the differences between different polynomials, as well as the differences between the terms of polynomials. So a polynomial means many numbers. So I could have a monomial that has one term, a binomial that has two terms, a trinomial has three terms, a quadrinomial, a four-term polynomial which has four terms. And each of these polynomials, if I were to put 1, then 2, then 3, then 4, and then 5, I would get a sequence of numbers like this one. 6, 11, 18, 27, 38, 41. And each of these sequences can be described by their differences. Like, for example, the first difference is this right here. You take the sequence of numbers generated by x equals 0, x equals 1, x equals 2, x equals 3 by substitution. So this one down here. So this is x equals 1, x equals 2, etc., etc., etc. I get that the difference between 11 and 6 is 5, between 18 and 11 is 7, then the next difference is 9, then 11, then 13. And then I notice my differences form a pattern in themselves, known as the second difference. And that second difference is consistently 2, which is very appropriate because when it has a constant second difference, it's a quadratic function or a power 2 function. Let's see if we can show that that works for all such functions of that type. For example, if we have a linear polynomial given by the expression ax plus b, where a and b are constants, it doesn't really matter what they are, but simply that they exist. So if we were to substitute 0 in for ax plus b, we would get b. If we were to substitute a, we would get 1a plus b. If we were to substitute 2a plus b, take a moment, complete that line of the table, then check back. Do you have the same thing here? Now let's see what happens when we take the first differences. So the first difference here between these two would be a plus b minus b. Well, b minus b is 0, so it's just a. Then here we're going to subtract, and I'll do this on the side here, 2a plus b minus a plus b. Well, the b's cancel, and 2a minus a is a again. What's the first difference here? Are you getting for a sense of a pattern here? Notice for a linear sequence, the first difference is constant. Constant first difference. And the second difference, if we wish to continue with this, a minus a is 0, 0, 0, etc. Now, looking simply at linear might say, okay, that's kind of interesting, but how is that unique? So let's examine the quadratic polynomial. Let that come into focus a little more. I've already completed some of this for you. Notice we take the generic polynomial, ax squared plus bx plus c, where we substitute in 0, therefore we get c, 1 we get a plus b plus c, because 1 squared is 1, times b times 1 is b, etc. We substitute in 2, we would get 4a plus 2b plus c. We begin to take the differences, and let's see if you notice what happens. Let's check the work already here. So a plus b plus c minus c, that's a plus b. Fair enough. Similarly, if we subtract these two, we get 3a plus b. You can already get a sense for what the pattern begins to look like, so that when we do the subtraction here and find that the next difference is 7a plus b is hardly surprising, followed by 9a plus b. So that when we continue to subtract to find the second difference, we find that the second difference is continually 2a. And it's the third distance difference in this case that remains constant. So quadratic polynomials have a constant second difference. Now, 2 points always make a line, so let's verify this with a third level polynomial, which is of course a quadratic. So if we examine is of course the cubic. So we take our generic cubic and we're going to find the second, third, and fourth differences of the polynomial. Notice, for the purposes of time, I've completed this for us. But you can always, please feel comfortable, go through to verify. And if you notice, the first difference seems to have 2 patterns embedded in it. The second difference seems to have 1 pattern embedded in it because 2b remains the same. And it's only the multiple of a that's changing. And by the third difference is where we get the constant change of 6a. The fourth difference is in fact 0. So we can say cubic polynomials have constant, that means unchanging, third difference. 3 points is enough to actually establish a sequence. So we can say in turn that if we have a generic type of relationship right here, we can actually make a substantial prediction about what type of equation, what type of polynomial would fit to this data. This is a very low-tech way of doing a polynomial fit that's also possible to do through spreadsheets, GeoGebra, and other more advanced materials, but let's just take a look at this. What type of relationship is a set of ordered pairs below? How do you know? Fill in the blanks to the table to help you decide. The first differences have already been computed for you. So let's see. 0, 2, 1, 1, 2, 6, 3, 23. So the difference between 6 and 23 is 17. Let's see if we want the difference between 58 and 23. That would be 35, I believe. Please always check my arithmetic. And then 117 and 58. Well, that's annoying. So I'm going to do 118 and 58. And that would be 60. So the difference here must be 1 less, or 59. 59. Now if I do the second differences between this, difference between 5 and 17 is of course 12. The difference between 17 and 35, let's see, 37 minus 17 is 20, therefore 35 minus 17 will be 2 less than that. Minus 17 will be 18. And then 59 minus 35, let's see, that's going to be 20 and then 24. Notice the difference between 12 and 18 is again 6. Between 18 and 24 is again 6, creating that constant second difference. This tells us that this polynomial must be a cubic polynomial because of the constant second difference due to constant, I'm sorry, I misspoke, third difference. If it has a constant third difference, it's a power 3. Now, how do we actually find an equation to make this work? Well, I already know that y equals ax to the third plus bx squared plus cx plus d. Now, I get a little bit one of these for free, since I already know that when I put in z, 0, I get out 2. I know when all of this is zeroed out, then y equals 2, which so that's going to be 0 plus 0 plus 0 plus d. Therefore, d must be equal to 2. I then can say, all right, That gave me one possibility, y equals a, and I'm going to leave this blank so that I can plug some stuff in, plus c plus something plus 2. So I can take my next point and I can say when I substitute in 1, I get, let's see, 1 equals 1a plus b plus c plus 2. That's one equation. And then I can repeat that same process. I can say, well, what happens when x is 2, to create another equation. So a equals 2 to the third plus b times 2 squared plus c times 2 plus 2. Well, all of that has to be equal to 6 because that's the output. So 6 equals 8a plus 4b plus 2c plus 2. And it's not so difficult to see how I could come up with a third equation. I'm going to spare you the calculations. If I substitute my third term, an input of 3 gives me an output of 23. I can come up with a third equation. Having come up with 3 separate equations and 3 unknowns, I'm now in a situation where I can solve for a, b, and c. Now there are a couple different ways to do this, but let's just write out the equations individually on a separate piece of paper. I really recommend, giving yourself space to sprawl here. So I'm going to take this equation, rewrite that. So that tells me -1 equals a plus b plus c. This equation tells me that 4 equals 8a plus 4b plus 2c. This equation, sorry, that should be a 2, the last one there, tells me that 21 equals 27a plus 9b plus 3c. Now, there are many different ways to do this. You could do it by substitution, you could do it by elimination. My personal favorite is elimination, so I'm going to double this and add it, multiply this by -2 actually, and then add it to here, and then when I combine that, similarly, you can do the same thing. Instead of multiplying by -2, multiply by -3, and you'll get something like, this takes us to the classic two variables and 2 unknowns, which I'm sure you know how to do. For the purposes of time, though, I'm going to share with you the answer is a equals 1, b equals 0, and c equals -2, which means our equation over here would be y is equal to x squared, b is 0, so we drop that term, minus 2x plus 2. If we take in turn substitute any of these in, we find that it in fact works. Hope this was helpful. I want to wish you guys a wonderful rest of your day.